So now it's time to finally put L'Hopital's rule into practice and play around with it. I personally enjoy L'Hopital's rule immensely. I think it's great fun. So hopefully you guys will too. Okay, so I'm going to take the limit as x approaches 0 of e to the x minus 1 over x squared plus 3x. Now, never forget, always try to substitute in first. You never know. Maybe I gave you one that you could try, right? Right. Always try sub in the value. In our case, it would be x equals 0. So that would be e to the 0 minus 1. Oh, that my e got weird there. Over 0 squared plus 3 times 0. That would be 1 minus 1 over 0, which is 0 over 0, which is indeterminate. Yay! Even if you don't show all of this, you do have to kind of make a note that it is 0 over 0. That's part of your work to show that you checked. I should make a note. Note. Always check with substitution for indeterminate form and note it. I should highlight that. I should have put that on in a box somewhere. So let's notate that. Always, always, always. You make a little note. I tried and it's 0 over 0. Even if you don't show all this work over here, you have to show this bit. Okay, then that means that we can say, all right, well, that is equal by L'Hopital's rule. You have to notate it either with an L apostrophe H or lope. That's what I do a lot, lope. All right, it is equal to the limit. You have to write that still because you haven't substituted anything. Limit as x goes to 0 of, and now the top one was f of x, and the bottom one was g of x. So I'm going to take f prime of x. The derivative of e to the x minus 1 is e to the x, right? And then the denominator is g of x. So when I take the derivative there, it'll be 2x plus 3. All right, now I will try to substitute. So that would be e to the 0 over 2 times 0 plus 3. When you substitute is when you can finally drop the limit piece, right? This limit notation has to be kept into the problem all the way until you actually substitute. It's just a common mistake students make. All right, so e to the 0 is 1, 2 times 0 plus 3 is 3, and that is the limit. Now keep in mind, you didn't have any algebra tricks that were going to help you with this. We have an exponential and a polynomial, so yuck, right? There wasn't any good way to do this without L'Hopital's rule. So thank goodness for L'Hopital's rule. We can, of course, verify graphically what we're seeing with our own eyes. Oops, it's this one right here. There it is. So there's our function. And again, that hole in there I put in. It's not originally in there. If you graph the graph, it'll, if you just put that function in, it'll think it's there. But if you let your mouse get really close and on top of 0, see what happens? It turns it undefined. Yeah, because it's not really there. But if I put that point in for where we just said it was, we just said it should be at 1/3, and look at that. It's right on top of that curve. So that is indeed the puncture. So we're verifying graphically what we're seeing, right? So that is verified graphically. We can see that that value is in fact at 1/3. All right, so that wasn't so bad. Let's keep doing it. All right, so let's check our form. So I'm going to try to substitute. And this one's a little bit tricky. I might actually want to show this one. Try sub in 2 pi, right? So we're going to substitute in 2 pi. So that would be 2 pi sine of 2 pi plus 2 pi quantity squared minus 4 pi squared over x, 2 pi minus 2 pi. Oh my goodness. And we know this isn't going to work out. It's a question of how does it not work out? Is it infinity over infinity? Is it 0 over 0? What's going on here? Well, remember that the sine of 2 pi is 0. So that's 0 right there. 2 pi minus 2 pi is 0. So it ends up with 0 over here And then we end up with 4 pi squared minus 4 pi squared, which is 0 over 0. So that's our form, 0 over 0. Okay, so yet again, trouble in trouble in little city. All right, so I was going to say Trouble in Big China because that's a movie. And Trouble in Little City is from a different movie and a play called The Music Man. Okay, so L'Hopital's rule, and again, you must notate. They're not actually equal, they're equivalent. So you have to notate that with a little lope over your equal sign, or an L apostrophe H. All right, so now I'm going to need to find the derivative. Now the derivative in the denominator is easy because it's just x minus a constant. The derivative of 2 pi is 0, so this is just 1 down here. So that's easy. Now in the numerator, you have a little bit of work right there because x times sine of x is going to need the product rule. Remember product rule from derivatives? So take the derivative of x, which is 1, leave sine of x alone, plus, now leave x alone, and derivative of sine is cosine, plus 2x, and then 4 pi squared, don't be fooled, that's a constant. There's no variable in there, so you don't bring the 2 down or anything. It's just 0. All right? Okay, so let's kind of, I guess we could just substitute, right? I could rewrite it. I'm not applying L'Hopital's rule, so I'm not putting a L'Hopital over this equal sign here. I'm just cleaning this up a little bit. So this is sine of x plus x cosine of x plus 2x. That's all. So if I rewrite it and I didn't use L'Hopital or apply L'Hopital, then I won't put a little L'Hopital over it. You only do that when you've taken the derivative, basically, of the numerator and denominator functions. All right, so now I will actually substitute. So I want the sine of 2 pi plus 2 pi cosine of 2 pi plus 2 times 2 pi. All right, now the sine of 2 pi, again, is 0. We said that right up here. So that's still 0. This is 1. So that means that I have 2 pi plus 4 pi, which is 6 pi. Now 6 pi, let's find it with Desmos. Right here. 6 pi is about 18.849, 18.850. And you can see right here that 6 pi perfectly fits that graph. When I put that open circle in, there it is. But I can also see numerically, if I let my cursor get closer and closer to that value, I can see I'm getting closer to that 18.8 something, right? It's getting down there. All right, beautiful. And of course, 2 pi is about 6.28. So sure enough, it verifies it graphically. And of course, if you're asked to verify graphically, you draw a nicely scaled graph, right? Everything nice and beautiful. Have your area shown, don't have the graph too skinny, don't have it too wide, and have everything nicely labeled. Now, I had said earlier that we could repeat L'Hopital's rule and use it multiple times. Now is the time. Let's practice it. It's really not too bad. It just means you're going to do it more than once. All right. So let me check my form. If I put infinity in here, oh, I don't even need to work at it. Look at this. So it's infinity to the 4th power divided by infinity to the 4th power. So that's infinity over infinity, right? So this is infinity. So I'm going to check my form. And I'm just doing it in my head. I don't really need to show the substitution all the time. So it's going to be infinity over infinity. Okay. So then let's use L'Hopital's rule. So according to L'Hopital's rule, this should be equal to the limit as x goes to infinity of, take the derivative. So the derivative of this is 12x cubed minus 2x divided by 24x cubed. Okay, well, if I put infinity there, it's infinity over infinity still. Okay, let's go again then. L'Hopital's rule. All right, so little L'Hopital's over here. Limit as x goes to infinity of, all right, derivative would be 36x squared minus 2 over 76x squared. That is still infinity over infinity form. So this is equal to L'Hopital's rule, the limit as x goes to infinity of 72x over 144x. That's still infinity over infinity. Now, some of you might be saying, screaming at me in your head or at your computer, I know what this is. I know what this is. Yes. You know what this is because in Calc 1, they basically have to kind of cheat your way across this. They give you a little rule for how to do these without actually having learned L'Hopital's rule yet. But L'Hopital's rule is why it works. I'll show you in 1 second. So it's 72 over 144, and 72 over 144, finally, no L'Hopital's rule. This is equal to 72 over 144, which is 1/2. Now, what's the trick that you all learned in Calc 1? So we'll make a little note. In Calc 1, your teachers basically, or your professors, whichever, your professors tell you to take the ratio of the leading coefficients, right? So they say use ratio. Because I should say this, it's because the degree of the numerator equals the degree of the denominator. If they're not equal, there are other issues. But if the degree of the numerator is equal to the degree of the denominator, then you use the ratio of the leading coefficients. Right? And so they tell you 3 divided by 6, which is 1/2, and you're done, right? But they're cheating, right? But L'Hopital's rule is why that works. They just didn't tell you in Calc 1, right? They were cheating. Your Calculus 1 teachers cheated. And I say that with no malice because I'm a Calc 1 teacher and I do this all the time. Like, I don't tell people where it's coming from. I'm like, don't worry about it. We'll worry about it later. But they're cheating. They're getting you out of having to do L'Hopital's rule because at the time you don't know it. Now, some calculus teachers do teach L'Hopital's rule, but sometimes they don't. So it just depends. And usually you don't learn L'Hopital's rule until after you've learned derivatives, and you always learn limits first. So they kind of have to cheat at that point. But there you go, right? So you use the ratio of the leading coefficients for limits at infinity, for the limit as n or x goes to infinity of that ratio, right? Like there. It's not all the time. If you're going to 3, then it might be a different story, but we're going to infinity. All right, so we learned that rule, but L'Hopital's rule is actually why it works, right? This is also 1/2. And you can see it on the graph. If I go to infinity over here on this graph, look at that value, right? I'm heading to y equals 0.5 right here, right? That's that y value. And of course, I can look at it on Desmos and see. Oh, if I have it. Here it is. All right, so if I let that y value the x value get larger and larger, right, because I'm letting x go to infinity, then that y value is approaching that horizontal line at y equals 1/2. So I verified it graphically. Which means we have learned that, hey, you can use L'Hopital's rule more than once. It happens all the time, in fact. We will frequently use L'Hopital's rule, twice, 3 times. In this case, 1, 2, 3, 4 times. We used it 4 times in this problem. That's all right. It didn't really make it that much more difficult. It just made it a little bit more tedious.